Hello, everybody. Good afternoon. We are here today to attend and hear the talk that Florindo Bevilacqua, a Ph.D. student from Salerno University, will present. Florindo is with us in our lab last 3 months, making his abroad PhD study in the frame of his PhD in the area of Chipless RFIDs, and he has a very interesting talk to present. Just an information, this study during these last 3 months is concluded at this period, and he has made this study under my supervision and supervision of Professor Vardaxoglu, who is invited a researcher in our lab last years. So, Florindo, the floor is yours. You can proceed. Thank you
for your introduction. Okay, thank you. Good afternoon to everyone. For me, it's a pleasure today to be here to present my research project conducted here at the WiCom lab. The topic on the talk, as Anthony said, is the Chipless RFID tags, the design, the manufacturing, and also the characterization. Before to start with the presentation, it is useful to define the outline of this talk. First of all, we'll be introduced the problem of the radio frequency identification with the main objectives of this research project. In order to explain how it's possible to design and also to explain the working principles of the Chipless RFID tags, it will be useful to introduce a simple structure made of half-wave dipoles. At this point, it will be possible to explain how it's possible to go from simulation to measurements by the manufacturing of the prototypes, and also to explain the measurements procedure and the measurement setup. After this, will be presented the main novelty of this research project, the procedure to design Chipless RFID tag with a size reduction as compared to literature approach. Also in this case, designed tag will be experimentally validated, and at the end will be also shown some open research issues about the development of polarization independent Chipless RFID tag, a very interesting solution for this kind of applications, and also the design and the characterization of embroidered Chipless RFID tag for wearables application. But now let me start with the talk. In the framework of target identification, currently the most used identification approach exploits the use of barcode. For barcode, an optical scanner is used to read the code on the item. This is a simple identification approach, but it shows some issues, as for example, a reduced read range and also reduced data capacity. And in this case, the identification approach is a manual identification procedure. Accordingly, nowadays, the target identification can profit of the use of the radio frequency RFID technology. This is an automatikless communication approach used to identify target objects. And in this case, the communication between tag and the reader can exploit radio frequency signals. It's possible to differentiate two kinds of radio frequency identification tags, the active tags and the semi-passive tags. For the active tags, there is an onboard source used to power onboard electronics and to radiate the response, the code associated with the tag, to the receiver. Instead, for the semi-passive tags, there is just an embedded energy source used just to power the onboard electronics, but the tag is not able to generate the signal by its own, but just can be scattered the wave impinging on the tag from the reader. Accordingly, due to the presence of antenna, chip, and battery, Both the tags are typically large, complex, and expensive. A possible solution try to have a simple structure and also easier to manufacturing are the passive chipless RFID tags. What is a chipless RFID tag? Chipless RFID tags are fully passive microwave circuits that encode the data in the scattered electromagnetic wave without exploiting any active circuit. This kind of tags can be produced with a lower cost, and they also show smaller size. The cheapest RFID tags are also called as radar cross-section RCS-based tags. The RCS is an electromagnetic signature of an object that allows to measure how much is possible to detect the object from a radar. A possible solution to design to have a chipless RFID tag is to exploit resonators like this over a carrier substrate, and the associated tag can be in the RCS of the tag. Each resonator can be exploited to create a notch or a peak resonance around a given frequency point. In order to have the code associated to the tag, the presence of a resonant frequency corresponds to a bit set to 1, while its absence corresponds to a bit set to 0. This is a new research activity, a new kind of research technology, the chipless RFID tag, and particularly up to now, the study about this chipless tag focuses on the procedures aimed to reduce the size of the tag, also increasing the amount of data encoded in a given physical area. Furthermore, it is also interesting to try to verify the reading capability of the tags to different angles of incidence and orientation of the impinging wave. This kind of research activity on chipless RFID tag can be exploited to meet the growing demand for wearable application. In this framework, it's possible to identify the following objectives for this research activity. First of all, has been designed solutions aimed to reduce the physical size of tags while still keeping the functionality and also the performance. And also a first design of an orientation-independent tag has been proposed. All the design tags have been manufactured and also experimentally validated by using the available anechoic chamber at the WiCom lab. The experimental validation of the tag has been also performed by taking into account the robustness of the tag to be read at different angles of incidence. At the end, preliminary steps towards an embroidered chipless RFID tag for wearable application will be also presented. In order to explain how it's possible to design chipless RFID tags, it is useful to introduce a very simple structure made of a single resonator over a carrier substrate. A practical way to realize the resonator in microstrip circuits is the use of an open-ended transmission line. This line can be realized over a substrate, and also a ground plane is taken into account in order to reduce the interferences, to improve the reliability in the communication between the tag and the reader. This resonator will behave as a parallel resonance circuit. Accordingly, the input admittance will be 0 when the length of the resonator will be twice of the wavelength in the substrate. In fact, it is also called a half-wave dipole. By using this relation, it is possible to see how it's possible to relate the length, the dimension of the resonator with the resonance frequency of the tag. Accordingly, by fixing the material, for all the proposed tag, the material will be this kind of Rogers material for the substrate, and by fixing the resonance frequency, has been possible to calculate the optimal length of the half-wave dipole to resonate at this frequency. After the analytical design of the tag, the behavior of this kind of structure has been also validated by using a numerical approach by exploiting a commercial electromagnetic simulation tool, the CST1. In CST, a monostatic simulation setup has been taken into account. But what does it mean, monostatic? In a monostatic simulation setup, the same antenna, the same probe, it has been used to illuminate the tag and to collect, to measure the scattered field. About the source setting in CST, a plane wave has been adopted to illuminate the tag, and by considering this reference system, the direction of propagation is along the z-axis. This is a normal incidence condition, and for this kind of dipole-based Chipless RFID tags, it is necessary to have the polarization of the electric field parallel to the half wave to the dipole line. In this case, for this reference system, the electric field is linearly polarized along the x-axis. Okay, by using CST, it has been possible to calculate the RCS of the proposed resonator, and by looking at the radar, the simulated radar cross-section, it is possible to find a notch resonance at the frequency resonance of 4 GHz. In this point, there is a faint field that is backscattered at the resonance frequency. In order to understand better the behavior of this kind of tag, it is also useful to show the surface current density at the resonance frequency, as is possible calculated also in this case by using the software. At the resonance frequency, it is possible to find a very strong value of the amplitude of the surface current. Look, and so the tag is activated, and the notch resonance will appear in the RCS. By looking at the current distribution, it will be possible to find the maximum value at the center and the minimum at the edge of the resonator, and accordingly it will behave like a λ/2 antenna dipole. But near the resonance frequency, for example at 4.1 GHz, there is a very low value of the amplitude of the surface current, and accordingly the tag is not activated. By exploiting the design procedure explained for the one resonator, it has been possible to design the multi-bit Chipless RFID tag based on the use of half-wave dipoles. In this case, a structure with 5 half-wave dipoles has been designed and also validated by using CST. Looking at RCS, it's possible to explain the coding technique for this kind of chipless tag. In fact, by the simulation, 5 resonances can be found in the working frequency between 4 GHz and 5 GHz, and to each resonator line can be associated the corresponding resonance frequency. At each resonance, a bit set to 1 will be found. But by removing, for example, in this case, one resonator, or in this case, this is the 4th resonator that has been removed, the corresponding bit will be set to 0. And also, by removing 2 resonator, 2 bit will be set to 0. Okay, up to now, we just explained how it's possible to design the chipless tag and also to simulate this tag. But how we can go to perform the experimental validation in the anechoic chamber, it is necessary to manufacture the prototype of the tag. In order to achieve this goal, has been exported the Gerber file from the CST software, and by using this LPKF machine, the tag has been manufactured by using the chosen substrate material, and the prototype has been and in this way has been possible to use the prototype to go through the experimental validation of the tag. Okay, in order to have the measurements have been performed in the shielded anechoic chamber, and in order to have the same setup exploited also in simulation, a monostatic measurement setup has been considered. Accordingly, also in this case, the same probe has been used to illuminate the tag and to collect the scattered field. The measurements have been performed by collecting the scattering parameter by using a vector network analyzer connected. The analyzer is at the outside of the anechoic chamber, and it is connected by using phase stable cables to the probe inside the anechoic chamber. looking at the probe, also in this case, it is necessary, as in simulation, to have the electric field polarized along the x-axis, along parallel to the dipole lines. This is a single port measurement, and accordingly, before to start the measurements, a single port calibration based on the use of open load as short has been performed. Classical RCS measurements approach exploits the use of the wideband or an antenna like this one. But for the tag designed in this working frequency and characterized during this research project has been designed and also manufactured and used another kind of probe, a smaller probe, an antipodal dipole probe, this one. But why this probe has been adopted? Because in this way, by using a smaller probe, has been possible to reduce the reflections of the probe during the measurements, and also to have at the measurement distance of 20 centimeters a better fulfillment of the far field condition. In this way, it has been possible to achieve a best approximation of the impinging plane wave. Before to start the acquisition of the scattering parameter, has been also checked the alignment between tag and the probe by exploiting a laser approach. But from just the measurements of the scattering parameter of the tag, has been not possible to see the RCS of the tag, and so to read the associated code. And accordingly, has been also taken into account a calibration approach. 3 sets of measurements are necessary in order to calculate the RCS of the tag. First of all, has been acquired just the measurements of the isolation. All no tag is in the chamber, and just the support, the reflection from the support, and all the support have been acquired in order to remove all the static spurious reflection. After this step, a second measurement is performed with a reference copper plate with a known RCS with the same about the same dimensions of the tag, and at the end, the scattering parameter of the tag has been acquired. Okay, by using this relation, once the 3 scattering parameters have been acquired, it has been possible to convert these scattering parameters to the RCS of the tag. And this is the calculated RCS for the 5 half-wave dipoles. But look, so 5 resonances, as were predicted by CST, can be found in the RCS, so it's possible to read the code associated to this tag. But looking at this, for example, the first resonance frequency, it is very interesting to see what's happened in this region, this working region, in the scattering parameter. For example, in this is a zoom near the first resonance, and looking at the frequency, the frequency region near the resonance, the scattering parameter of the tag shows a very similar amplitude value as compared to the scattering parameter of the isolation. Accordingly, a very low value of the field is backscattered at this frequency, and the resonance will appear in the RCS of the tag. This behavior will show for all the resonance frequency. These measurements are measurements based on difference of very low values, so are very sensitive measurements approach. It is also very interesting to compare the frequency resonances measured by the experimental validation, this one, and the initial frequency resonances in CST. As it's possible to see, there is a little shift in the resonance frequencies by measurements and CST model, but after a microscope analysis has been found that these deviations can be explained due to small errors in the manufacturing of the tag. Accordingly, by taking into account these errors in the manufacturing, in the length of the dipoles, also in CST, has been possible to find a better agreement between the measurements and the simulation. Okay, but now the question is, how is possible to try to reduce the length of this kind of Chipless dipole lines? A literature approach suggests to replace the half-wave dipole line by using a lower, a smaller structure, but periodically loaded by using capacitors. In order to have a planar circuit, the loading capacitors can be realized by using open circuit stub. The critical parameters necessary to design this kind of structure are the length of the stub, the distance between the capacitors, and also the value of the loading capacitance CP. Okay, in this way, it's possible to have a reduced structure in the length with the same physical behavior, electrical behavior of the half-wave dipole, but it will be an increasement in this direction. And how is possible to try to reduce also these dimensions, but still keeping the same reduction in the length as compared to the half-wave dipole? A possible solution investigated during this research activity can be exploit the use of stepped impedance resonator. What is a stepped impedance resonator? A stepped impedance is a transmission line realized by alternating sections of very high impedance, accordingly a reduced width, and sections with very low impedance and higher width. Under the hypothesis that the electrical length of the low impedance transmission line are twice as compared to the electrical length of the high impedance transmission line at the resonance frequency, it is possible to find this relation to link the length of each transmission line to their frequency resonance and to the impedance ratio. What is the impedance ratio? The impedance ratio is the ratio between the low impedance line and the high impedance line. Accordingly, by properly choosing this impedance value sufficiently lower than this high impedance value, has been possible to achieve the reduction in the length as compared to the half-wave dipoles. But this value, the width of this low impedance line, should be lower than the corresponding dimension, vertical dimension for the slow wave resonator. By taking into account these design constraints, the stepped impedance resonator has been designed to work at 4 gigahertz, and the design tag has been also numerically validated by using the simulation in CST. Looking at the dimension, has been possible to find to obtain a reduction of about 68% in the vertical dimension as compared to the corresponding slow wave resonator, and the reduction in the length of the half-wave dipole is of about 25%, the same achieved by using the slow wave resonator approach. And also in this case, looking at RCS, a notch resonance can be found by using the simulation in CST. For this kind of structure, it is very interesting to see the current distribution at the resonance frequency. In fact, also in this case, as for the dipole, half-wave dipole resonator, the current distribution, the current surface is like the λ/2 dipole, but so this structure shows the same electrical behavior of the half-wave dipole, but the length is reduced. By using the explained design procedure, the 5-bit stepped impedance resonator has been also designed and numerically validated to work in the same working frequency of the half-wave dipole between 4 and 5 gigahertz. Looking at the dimension, by using this approach, has been possible to reduce the physical area of the tag of about 34% as compared to the corresponding slow wave tag working in the same frequency region. And looking at RCS, 5 resonances can be found, and so it's possible to read the code associated to this stepped resonator. The proposed tag has been also in this case manufactured by using the LPKF machine and experimentally validated by using the same setup previously described for the half-wave dipole Chipless RFID tag. And also in this case, at the beginning, there was some discrepancies, lower, an error of about lower than 2% at maximum for the measurement for the resonance frequency, comparing the measurements and the CST value. But also in this case, by using a microscope approach, has been possible to explain that these shifts in the resonance frequency are related with some errors in the manufacturing of the tag, and by taking into account these errors also in the CST model, a better matching, a very good matching between measurements and simulation has been found. Okay, the other interesting experimental validation has been also performed by taking into account different distances between the probe and the tag. In this case, we are interested just to find the resonances position, the resonance positions, and looking at the difference between the scattering parameter between the tag and the isolation for all the distance between 15 centimeter and 35 centimeters, 5-notch resonances coding the tag ID can be found by the experimental validation. Design chipless RFID tags is a very complicated approach. Also, the choice of the material substrate is a critical parameter in this kind of application. For example, the same stepped tag has been also designed, simulated, and manufactured by using this kind of substrate material, the taconic RF30. This material is too elastic to be manufactured by using our LPKF machine. And looking at the RCS, at the measured RCS for this tag, we can compare the results with the stepped resonator for the Rogers. And by exploiting the experimentally Q factor, the Q factor is a parameter used to measure the quality of a resonance. Higher Q factor can be found for the Rogers tag, and accordingly a not effective manufacturing could make the identification approach not possible in actual measurements. Finally, starting from the design of the 5-bit has been designed and manufactured and characterized the 10-bit stepped impedance resonator. In this case, by the experimental validation, 10-notch resonances can be clearly found in the RCS, and accordingly, the 10-bit one can be found and the code can be read. In this case, also the shifts between simulation and measurements are lower than 2.5% since small errors in the manufacturing. In this case, the working frequency is between 4 and 6.25 gigahertz. It's out of the working frequency of the antipodal dipole, and accordingly, the classical wave, the classical horn antenna has been used for this kind of measurements as probe. Up to now, the experimental validation has been performed just considering the normal incidence between the probe and the tag. But it is also interesting to verify the robustness of the tag to be read at different angles of incidence. Accordingly, by using this setup, these rotating tables, has been possible to change the angle of incidence between the tag and the probe, and by the laser has been possible to read the value of these angles. These results will be the results presented has been compared with the CST predicted results for the angle of 0, 30, and 45 degree in the vertical, in the horizontal cut for phi 0 and theta changing. And by the comparison between simulation and the experimental validation, a good agreement also in this case can be found. In fact, it is possible to clearly read the 5 resonances up also for an angle of 45 degrees for the angle of incidence. So the code of the tag is possible to read this code also for this angle of incidence. The same simulation, the same validation has been also considered for the other cut, the vertical cut. In this case, has been rotated both the tag and the antenna. And these are the results, the comparison between simulation and the experimental validation for the angle, also in this case of 0, 30, and 45. And also for this cut, it is possible to clearly find the associate code, the 5 resonances, also for the angle of 45 degrees. As already stressed at the beginning, in order to have the possibility to read the code for this kind of dipole-based tag, it is necessary to have the polarization of the electric field parallel to the half-wave dipoles. For example, in this case, in the anechoic chamber has been rotated just the tag. Accordingly, the polarization of the field is orthogonal to the half-wave dipoles. And by looking at the measurement at the RCS, at the acquired RCS, no code can be read by using this kind of measurements setup. Accordingly, this is a polarization-dependent structure. In order to try to solve this problem, this issue has been also designed and simulated a circular, asymmetrical resonator, the circular resonator. In this case, it's possible to relate the radius of the circle with the working resonance frequency. And after the design of the tag, the circular resonator has been numerically related by using CST, and for both the polarization, can be found the same notch in the resonance frequency. And by looking at the current distribution for both the polarization, the surface current density is like the lambda dipole antenna. Starting from this design procedure, has been also manufactured and characterized the 4-bit circular resonator. Looking at the resonators, each circle can be nested one to each other in order to physically implement the tag ID associated with this code. The tag working frequency is between 4 and 7 gigahertz, and also in this case, from the experimental validation, 4 resonances can be clearly found in the RCS, and accordingly, the associated code can be found. All this research activity about chipless RFID tags can be also exploited to design chipless RFID for wearable application. But why it is possible to use the chipless RFID in this framework? Because the absence of the integrated circuits and also battery makes this tag less prone to damage from heat and also washing procedure. And furthermore, there is a possibility to design the tags for flexible substrate in order to be applied also in clothes and bags and other fabrics. A suitable solution to realize chipless RFID tag for wearable application is to use the available embroidering machine. What is an embroidering machine? An embroidering machine is a machine specialized that in the manufacturing of embroidered designs by using conductive thread. Our interest was in design a dipole-based structure by using the conductive thread. Accordingly, as we need to use 3 different kinds of layers. The first layer is the substrate layer, the cotton, where the embroidery machine can manufacture the conductive yarns. The second substrate layer is a felt material, where it's possible to attach the ground layer, in this case, a conductive textile, the Noradel one. But in order to design the half-wave dipole, we need to know the overall permittivity of this substrate, the substrate made by the union of cotton and felt. In order to measure this value, has been exploited a cavity resonance, and by putting in this cavity resonance the union of the cotton and the felt by using a Q-meter, has been possible to calculate the overall, the effective epsilon of the material and also the losses. At this point, by using the design procedure, and has been designed, analytically designed, the 2-bit embroidered tag, and has been also simulated by using the CST. To have a better model of this kind of tag, has been also taken into account an effective value of the conductivity for the conductive yarn. The working frequency of this kind of tag was between 4.5 gigahertz and 5.5 gigahertz. After the simulation, the embroidered tag has been manufactured, and by using the same approach also for this kind of tag, the measurements procedure is still the same. Can be shown the comparison between measurements, this line, the orange line, and the simulation. It is very interesting to see that also, as predicted by the CST model, 2-notch resonances can be found also in this case. Each resonance it's associated to each conductive yarn in this embroidered tag. To have a better matching between measurements and simulation can be also taken into account that for this kind of conductive material, the ideal conductive path is not flat as the ideal one, but there is the roughness problem. There are these deviation in the conductive path. By taking into account this problem, also in CST, can be possible to find a better matching between measurements and simulation. Of course, this kind of application is a new kind of research study, and accordingly, further investigation will be necessary to obtain better performance in the coding procedure of the tag ID. To conclude, Chipless RFID tags design, manufacturing, and characterization has been presented in these talks. First of all, design solutions aim to reduce the physical size of tags, but still keeping the same performance and functionality has been introduced. Then this kind of tags have been manufactured and also experimentally validated. In order to solve the problem of the polarization dependency of dipole-based tag, also a symmetrical structure based on the use of circular resonator has been proposed. Preliminary steps to design embroidered chipless RFID tag for wearable applications has been also presented. Let me now thank Dr. Alexandridis, Professor Jan Vardaksoglu, and all the staff of the WiCom lab for the possibility of this kind of research project, and also my professor in Italy, Professor D'Agostino of the University of Salerno, Professor Capozzoli, Curcio, and Professor Piseno from University of Naples. Thank you everyone for your kind attention.
Thank you very much, Florindo. Very nice presentation. If there are questions, Paris.
Well done, Florindo. That's a lot of work for 3 months.
Thank you.
Very interesting work. Could you please go to slide 15?
Yes, one moment.
Okay.
15.
Yes, yes.
Yeah, will you explain why you use the antipodal dipole instead of using the horn antenna? You say that the far field of the horn antenna is 243 centimeters, and the antipodal dipole is 53 centimeters. So what is your basic condition, that you need to be on the far field?
We need to be as much as possible closer to the far field.
The 20 centimeter distance is the Fernando, is propagating nearly.
Yes, but
it's not reactive.
It is not reactive, but it's enough to
propagating.
make this kind of measurements. But we have in this case, for this condition, even if we are not in the far field, there is a better approximation of the impinging plane wave comparing with the horn antenna at the same distance.
Yeah, but anyways, you would get some results if you could decrease the reflector behind the antipodal dipole to achieve the lower far field distance. So
yes, of course.
Measurements in the far field.
Yes.
But you don't think that these measurements could create you any problem?
No, I think it's enough to this distance. We try also to make the same characterization also in not so close, and we have the same results. So.
Okay. Okay. In the equation of the radar cross section, you use only the magnitude, not the phase.
Just the magnitude too.
Okay, that's why
we acquired the complex.
Okay, because the phase. Okay. Okay. And in slide 26. Okay, here. I have 2 questions here. First of all, the other extra resonance
this is not a resonance frequency. It's just a fluctuation in this difference. It's not because this kind of this difference, as shown. Can I go back in for the slide to show you better? Look, he looks clear near the resonance. We are just the difference between the scattering parameter is very low. So when we make the acquisition, also it's very sensible to this kind of difference, to some changement in the difference between the ISO and the tag.
Okay.
So this is not an extra resonance. Yes, it's just a reflection. Let's put it. No, we use it's just for show the peak the setup, but we use the antipodal dipole for this kind of measurements.
Okay, and the last not question, just the notification that this chipless RFID tag is stable in terms of information propagated. For example, this is 5
yes.
1 bit
is,
0. Okay.
Yes, is one
like just standard for a card in a factory for entering.
Yes.
Just a standard bit called
this. Okay, thank you.
Very good work.
Thank you very much.
Something. Very good work and very good presentation.
Thank you.
I think on slide 12, it's about the circular resonator.
Circular resonator?
Yes. It wasn't very clear to me what was the problem here on the measurement. You said there was a problem with the orientation of the measurements.
Yes, in this case, look at this. To explain this one, we need to come back here.
Okay.
For the dipole-based tag, it is necessary that the orientation, the polarization, the linear polarization of the electric field in order to activate the tag and so to have the resonance in the scattered in the RCS, the electric field should be parallel to the dipole line.
Okay.
Yes, the dipole electric field. In this case, this is orthogonal. So no resonances can be found in the scattered field. For the dipole structure, this structure shows an symmetric behavior, symmetric structure. So even if when the electric field is along the y-axis, it's polarized along the y-axis, and also on the x-axis for the normal incidence condition. Yes, in the two linear polarization.
Not circular.
No, it's a two linear polarization. You can find for both this polarization, the same resonance condition.
Could I ask something? Someone maybe could use, instead of the circular shape, a cross shape, for example, instead of this.
Yes, I think that it could be also.
Maybe you need more space.
Yes.
To extend. Okay.
But this one, the ring, you can take any angle.
Yes.
Yes.
Very horizontal. So it's quite
interesting to use it.
sensitive
Incidence to polarization.
And what about the physical dimensions? Are the same with the?
Yes, are about the same. In this case, this case is very interesting because you can put the resonator one to each other, and the grooving in the frequency, you can have a reduced circuit that you can nest inside this by using the same dimension of the 4-bit resonator.
Okay. So someone would say this is a better choice.
This is a yes, it could
As
be.
I understand it.
Yes, it could be a new kind of research project about this kind of structure.
Okay.
It's very appealing a solution.
But it's with a wide
Yes,
frequency.
you need a wider frequency bandwidth.
Yes.
You gain something, you lose something.
Yes, there is always this trade-off between.
No, this is really good.
So, Florindo, what about the distances between the dipole and its ring?
Yes, the distance
What
is
about the
is
capacitances of
the distance is a parameter to take into account during this simulation. In this,
assuming they are close enough.
yes, there is a problem with the mutual cap
will,
will be too much closer, and you can also lose some resonances in the manufacturing. So in the simulation step, you need to try which is the best distance to have.
by parametric
Yes,
analysis
yes,
to find the discrete resonances.
yes,
Also because of coupling.
yes. Exactly. This is a problem. There is in fact, for the coupling, looking at the position of the resonator, on the substrate. It is interesting to show also this point about the coupling. Thanks for the question. Because in this case, can you see the half-wave dipole 1 is not close to the half-wave dipole 2. So two near resonances on the substrate are not on the scalar RCS are not close in this case to the over the substrate. So this has been taken also into account this point to try to reduce as much as possible the mutual coupling between the resonators.
Also half lambda between the dipoles.
No, this is no. This space is not half lambda. It's been just found the optimal space between the dipole to try to reduce to have to avoid too much coupling and to have a reduced size of the tag. This is a trade-off condition.
And the optimal place
in this case
is derived through parametric
yes,
simulation.
Parametric simulation by using the software.
Yeah, do you have an estimation for the distance between the?
Yes, it's in this case for all the tag has been used. From this point to this point, the distance is of about 2 millimeters.
What in terms of lambda?
Yes, it should be about lambda over 10, not so enough.
10.
Yes.
Okay. If it's too close, then you lose. There's too much coupling. If it's too wide, then you. So it's. I think you optimize this.
Yes, we optimize.
So you did an optimization.
Okay, so there is coupling, but you use it. To, you have coupling,
yes,
but you use it. You do not want to have full isolation.
No.
So you have coupling, but you use it in order to select your frequency.
Yes.
Right? Okay. Nice.
Well, I have a comment and a difficult question. The angles of incidence in a practical application, how do you say, maybe that's a difficult question. How do you see in a practical application this working?
In practical application.
Yeah. I mean, if it's on a cloth, you go through some reader. I mean, how do we, it's also for everyone.
Okay, so the way to try to have this kind of angle of incidence also in practical application.
Yeah. I mean, it's related to the angle of incidence.
Yes.
I mean, you know, you're going through something and it reads the tag, or you scan it.
Yes, particularly when you scan the tag, you are not. It is not mandatory to have the same alignment between the tag, the reader in this case, and the tag.
Yeah.
Also, for example, for the inventory tracking, I use this kind of reader. You can use a more flexible identification approach. You don't need to have this strict.
So you don't need to go over it.
Yes.
Like you can do it.
Yes, you can.
Which interesting. It's quite stable.
It is very stable.
Not so stable.
In fact,
so at an angle, you can read it at an angle. That's the idea, yeah.
Yes.
In fact, I have inverse idea in my mind because there is a steady reader, and you have a card as an entrance card, and you approach with a card the reader. So the problem is if it is necessary to approach the card like this or in an angle. Okay, so this proves that you can approach the reader in an angle, and it is also quite insensitive.
And as you get it closer, then you're normal. You know, you approach the reader, getting closer, and
But the other,
so it will read you before you. Before you're normal.
Yes, but the other concept where you have somewhere the tag, and you approach the tag with the reader, as you saw before, if it is something on the cloth, on a arm, and you approach the reader, maybe there are more restrictions on how you can do this.
So, and on the surface roughness, and this
Yes.
is related to the work these guys are doing. CST, what is the CST model for the surface roughness?
Yes, it's just a root mean square value of this kind of roughness.
So it assumes is some sort of periodic.
Yes, it should
not irregular.
Yes, it assumes some periodical roughness in the conductive yarns. Just take in this case the root mean square value to have an estimation of this kind of.
And what value did you take for that one?
Yes.
Do you remember?
Yes, of course.
Because that's interesting. The work.
Yes, this is interesting. In fact,
we use this kind of value for
0.1.
Yes, 0.1.
100 microns.
Yes.
Yes.
But it is interesting to know exactly the model that the CST is using to put this parameter.
Yeah, I think maybe.
It is.
Is a normal distribution. I think it's a random normal distribution.
Maybe it is
statistical
RMS error or something.
noise. Yes,
Like noise.
Yeah. But in the electromagnetic, in the surface area. So it will probably play around with the conductivity as well. Yeah. Yeah, that's good actually. It looks very rough there. I mean,
Yes.
That's the best.
So might not be periodical.
No.
Statistics.
Statistics.
RMS error.
It assumes a statistical distribution.
Very large.
Yeah.
Okay.
We have a question.
There you are.
Okay.
Everyone has a
Mr.
question. That's good. Mr.
Mr. Thermopoulos, you are here?
Yeah, from.
Hey.
Hi.
Hey.
Hi.
I just ask a question if I can ask the questions rather than writing in the chat. First of all, I would like to congratulate Florindo for an excellent work and the entire team. I think what is very interesting is that it's from A to Z, from the theory all the way to the implementation and testing, which makes it really very interesting. So congrats. A couple of questions. I'm not in the field, but I've been working with RFID tags and how we can use them for security projects. So I would like to ask some probably more practical questions. Probably I'll ask them all and then you can reply to one by one. First of all, are these tags reprogrammable, or once you burn them, quote unquote, the signature cannot change? Second question, what is the data density that you can store in these tags, and how much you anticipate would cost to manufacture? And that's the third question. The fourth one, would it require new types of RFID readers to read the data off them?
Okay, thank you very much for your interesting question. Let me try to answer starting for the first question. Okay. First of all, about the coding associated to the tag. Let me go back to this slide. Okay. At the beginning, the code is a fixed code over the same substrate, because to each resonator you physically associate a line, so you can just change the number of the bit coded over the same surface. In this case, just removing one or more than one resonator. But the resonator is physically associated to this signature, to each, just is associated to each resonator over the substrate.
That was the first question.
This was the first question.
So it's not.
So you cannot
It is not
reprogram.
programmable. Yes.
Not as it stands.
As it stands.
Yes.
But you could break, I don't know if this guy can hear me, but if you break the dipole,
Yes.
you put a diode.
You can make it programmable by
and
the
you
voltage
read-
on.
you put some voltage across,
Okay.
Yes.
and you switch it on and off.
You
Yeah.
can change.
And then if you put diodes in all of them,
You can program
and then you can modulate.
You make it an RIS.
Yeah, then
You
you
make
make
it
it.
an RIS.
But
Yeah.
then
Yes,
But it's
yes.
not more cheap.
Sorry,
But
about
it is not passive.
It's
Then
not more passive chip as is.
It's passive.
You need a chip to do that, so it's
Yes,
not,
you need a chip.
It's not a chip,
And diode.
and it's
That's
not
the
cheap.
And diode.
Diode.
Okay, all right.
So it's not a cheap as well,
Yeah.
yes.
but in that case, and then you can modulate it, and then you can program it. So that's further down. But I don't think you need that. It depends what application you have.
Yes.
So, yeah.
It's a trade-off. It's a trade.
Yeah.
The physical state of this kind of RFIDs is to be not to be programmable. Is
Yeah,
To be fixed to
fixed.
but if you want to change,
If you want to change, you have to
you have to make another one.
to subtract one
And
of
it's cheap enough to do it.
to change.
And
Roll it.
just try to answer to the other two
Yes,
questions.
we're gonna-
So if I could, I may follow up a little bit on that one. During the manufacturing process, then you have to encode each one of the different codes on the tag as you manufacture it. So you get a batch, and each one
Yes.
of parts. All right. Okay. So you cannot go back and make corrections. All right. Okay.
And the second question was about the density of the bit over the physical area. This is up to now we just try to reduce the size, the area of the classical approach using literature. For example, the dipole by coding the same. For example, the slow wave approach, this one by coding the same number of bits in the same physical area. But of course, if you are able to reduce as much as possible this area, you can try to put more bits, so more resonator in the same physical space as compared with a grid with a gridded structure.
Yeah.
Okay.
And the third was about the security, about the reader, the changement in the equipment necessary with this kind of.
Yeah, well, you need new,
Yes.
new equipment.
Yes, probably at this stage we are just in looking for how it's possible to detect by the experimental validation these resonances. So we are using just the classical DNA approach to measure these resonance frequencies. But of course, it will be necessary for the practical application to try to have a different identification approach to try to make it actual in the application.
I think there will be some sort of calibration.
It is necessary the calibration.
You set up the reader,
Yes.
and then you calibrate it for that vicinity, and someone goes through, you will read it.
Yes, and it is
Yeah.
also interesting.
I said the answer is probably yes.
Yes.
You will need new equipment.
It is interesting that you can just make the calibration by subtracting the isolation
Yeah.
with the tag when the tag is put on.
And you can update.
Yes,
because you read
you can update this
you can
value.
keep updating it.
Yes.
So yeah.
Thanks for your question.
Does this answer it? Is it
Thank
answer?
you.
Okay, excellent.
In
Thank you.
And
There was another question by. Okay, okay.
okay.
So we finished. Yeah. Can I just say that this is an excellent work. I mean, he did this. He came January
At the half of January.
after New Year.
Yes.
And had Easter in between. It's only less than 3 months. How many days?
3 months of about 6 days of work.
Yeah, so it's fantastic. Just well done to Florindo and
Thank you for all the stuff.
Adonis,
I agree with you,
and
yeah.
Paris.
I
You know,
agree.
this is, and I've seen a lot of PhD students in my time, also using a fantastic environment, okay? Because the lab here, the measurements, you know,
Yes.
and this is good stuff, guys. You know, it's international standards, you know, so I congratulate you.
Thank you, and thank
Okay.
you for the
Thank-
WiCom Live.
Thank you,
Michael,
Florindo.
It has been a pleasure for me to be
You will
here.
learn a dinner tonight, please, in my sailing club down in Animos. So.
Okay.
So,
Thank you.
And also you have to see Acropolis in between, yeah, and Studio. So fantastic. Well done. I'm really.
It's been a
pleased
pleasure
about
for
it,
me
yeah.
spend this time here in
And
Greece.
I'll go in September, October.
Yeah, in
I'll go
October,
to
yes, you
Salerno
will be in
as an
Salerno and
visiting,
Naples.
Yeah. I'll be visiting Salerno, so we carry on some of this stuff there. Yeah. Good.
Okay.
okay. Thank you, Florindo, again.
Thank you again.
Thank you, everybody, for your attendance.